As the demands for AI processing reaches new heights, the quest for sustainable semiconductor solutions becomes more critical than ever. This next panel will explore how semiconductor industry is making monumental strides to ensure efficient AI processing while minimizing environmental impact. In conversation with Vice President, Hardware Catalyst Initiative at VentureLab, Avinash Persaud, please welcome angelpreneur, angel investor, serial entrepreneur, and chip design engineer, Raymond Chick, and co-founder and CEO of Lemurian Labs, Jay Dawani.
Thank you. Welcome to the Sustainable Semiconductor Solutions with AI panel. I'm Avinash Persaud, Vice President of the Hardware Catalyst Initiative at VentureLab. We designed a 2-year program that supports semiconductor startups along with sensor technology startups and microelectronic startups. If you're interested and want to know more about any of that, please reach out to us at venturelab.ca. As I was backstage, it occurred to me that at some point in the future, maybe we have 3 AI chatbots up here conducting this panel. It'd be interesting to juxtapose what they come up with versus what we discuss here. But I have a high degree of confidence in the expert panelists that we have joining us today. So for now, I look forward to that. I'll start off with asking Jay Dawani to provide an introduction to himself first, please.
Sure. My name is Jay. I'm the co-founder and CEO of Lemurian Labs. I've been working at the frontiers of AI for about 10 years, including on some of the things that most of you have heard about in the news. And I started Lemurian to try and make general purpose autonomy a reality, only to run into a roadblock, which was computing. And so decided to fix computing. At a high level, that's it.
Thank you, Jay. And Raymond Chick?
My name is Raymond Chick. As you have heard, I call myself an engineer first. I've been a chip design engineer for 30 years. And then had entrepreneurial things that I did, startups and whatnot, a few of them actually over the course of past 20 years or so. And most recently, I'm passionate about angel investing and helping deep tech startup to get them going. And my latest startup, Untether AI, has been around for 5-6 years. And for those of you who have been here since this morning, might have attended my colleague's panel session. Bob Beechler talks about AI. And so that's where I am.
Thank you, Raymond. My first question I'm going to put to you, Jay, and it's in 2 parts. The first part is, why are AI application-specific semiconductors needed for sustainable semiconductor solutions? What will they deliver differently to generic GPUs and TPUs? And I also wanted, if you didn't mind, to explore a little bit more what's meant by GPUs and TPUs.
Sure. So first and foremost, you need a chip to run any kind of software, right? And more importantly, you can think about computing, and a semiconductor specifically. It's actually really simple. It comes down to 3 things. You have math, because all computers do is calculate, and they have number representations in which they store all the information. They have storage of said information, and then they have movement. Now, the thing that differs between all of these different kinds of computing is how they are organized. So sometimes you have a single math unit, you have a single memory, you move data back and forth. Sometimes you have a vector of these things, and sometimes you have a matrix. Now, the thing that differs between all of this is, again, structure. Computing hasn't really changed in about 70 years. So the GPU is still predominantly what is referred to as a von Neumann processor. And it has very, very, very old legacy problems. The TPU tried to address some of that by building something that was primarily really, really good at doing matrix math. Because when you think about AI, it all boils down to just doing a lot of matrix math. It really is just that simple. Now, the enormity of those problems is a whole other thing. And that's why we're thinking a lot about chips today. We've seen about 1,000,000x growth in compute requirements in the last 10 years. And computing has only evolved and given us about 1,000x in 10 years. So that gap keeps getting bigger and bigger and bigger. And that is a big problem because now as the requirements of compute get bigger, you need more compute to try and sustain that. And that consumes a lot of power. So at the end of the day, computer organization matters a lot. And that's something we think about as well, a lot, because we have semiconductor companies. But there's a lot of opportunity to deliver something new, and that math hasn't changed in also 70 years. How you move data around hasn't changed in 70 years. How you program these chips hasn't changed in longer than that. And I think it's about time, now that things are breaking and literally setting on fire, we should be sort of thinking about this. Because otherwise, we really don't have to worry about AI or some future scenario of killer robots, because trying to train these models is going to come and get us first.
Thank you. Raymond, my question to you is about semiconductor solutions of any scale require significant investment behind it. As someone who's been involved in semiconductor development as well as an expert investor, what do you see as the opportunities for investment? And can you tell us about your involvement with the Hard Tech Investor Network?
Sure. With hardware startups and semiconductor startups and whatnot, first of all, being a founder of a semiconductor startup, lived through the fundraising round, and it's not easy. And it takes a lot, because a lot of investors, especially in the Canadian VC community, mostly are very conservative, and a lot of them are more comfortable in investing in software startups, because number one, comparatively speaking, hardware is much more capital intensive. You build a chip, especially the advanced nodes, the compute, what Jay is building, what we're building in Tether AI, it easily takes you a few million to $10 million to just go one try. So it's a lot of money involved. And for software, not trying to say it's an easier task, but at least if you make a mistake in software, it's much easier to get around and fix it. You make a mistake in the chip, $10 million down the drain, and you have to do it again. And the cycle time is also long too. You make a chip, you send the chip to TSMC or Global Foundry to fabricate, comes back 3 months later. So you can see the cycle is very long. The horizon of investing in a hardware company, a semiconductor company, is not like 5, 6 years. You're looking 7, 8, 9, 10 years.
Yeah,
so
there's a little bit more to that as well, right? So there's a common fallacy that I've seen with investors, and that's they think hardware takes more, but if you actually look at it from the grand scheme of things and you sum up all the amount of money that a company's had to raise for software and hardware, it comes out on about par. The only thing is that hardware needs more money up front than software does.
Yes. But it's a more short-term view. The software kind of gives you a safer sense when you put money in there.
And yet, Raymond, you still see the opportunity. So I'm intrigued by what are those opportunities beyond these obvious initial problems that you see as rewarding?
Well, the opportunity, I guess I would add on to the point from investors' perspective. Investing in hardware often means that the moat, the barrier of competitor entry is much higher. So you've got a lot of time when you build a chip, you have a lot of IP around it, you have a great idea, but in order to get to that idea, you have to, if you are a year or two ahead of other people, it's hard for other people to copy your idea and be competitive with you. So therefore the moat is stronger, and therefore to me it's more investable. It's safer that way, and opportunity-wise, everybody is trying to invest in AI, obviously, and there's a big opportunity in AI hardware there. As Jay's company, as my company, has been quite successful in raising funding to build new chips, new way of doing things to accelerate AI, as compared to the GPU, which is the king now. But we're all trying to provide a alternative or better solution to that. So there's a lot of opportunity in investing in that area. But not only that. The AI and semiconductor is sort of the sexy area nowadays. There's a lot of things in the semiconductor industry that you can invest into. For example, power management ICs for AI,
Right.
And energy management, because as Bob earlier was saying in the other panel, AI is going to take up a lot of energy in data centers. So how to manage that?
Right.
It's also other types of semiconductor you could.
This is another time that I'm hearing reference to semiconductors are sexy. I wish it was earlier in my career, but Jay, my next question to you is, we're now immersed in generative AI like ChatGPT. What are the unique aspects of generative AI, and what comes after, and how will semiconductors make that a reality?
Yeah, that's a lot of questions. So firstly, generative AI has been around for a very long time. It's been around for 4 decades almost. It's just only now that it's started to work, and the reason it's working is because of 3 things. The transformer architecture. It is magnificently scalable, which has always been an issue. And because it is scalable, it allows you to leverage a lot of compute. And to actually make something trainable, you need a lot of data. Thankfully, we have all of that in abundance. And if you can basically scrape the entire internet and feed it into a model, you can learn a lot. But that doesn't mean this model is as creative as people think. Right? It's still sampling what it already knows or has been fed, because these models memorize. They haven't really generalized, and generalization is what's key here. So I still believe, and I'm still really hopeful, that there will be more innovation in the space. There's 9 different efforts that I'm currently tracking or involved in that are looking at how do you address some of the limitations of the transformer. And I think in the next 4 years, the transformer is not the thing that we'll be talking about. We'll be onto something much, much cooler. So there's that. And what this thing is going to be able to do is essentially have a ground source of truth, a world model of sorts. The generative part will still be there, and that it's going to project or try and predict a future scenario from where it's currently at. It'll have a discriminator attached to it to help it reason about what the best opportunity is, and it'll keep doing this loop over and over again. Now, I came up with this theory of transitions in software a long time ago, which is largely holding true, interestingly. And it's every 3 orders of magnitude, we will see a new transition in software. So Andrej Karpathy, who used to run AI at Tesla, and we founded OpenAI, he came up with a software 1.0 to 2.0 transition. So you wrote code a certain way, and you dictated how you want the data to be manipulated with the algorithm. And what you had at 2.0 was you fed in a lot of data, and this model learned from that data how it should treat it, which is really interesting. And now we have software 3.0, which is generative AI, what everyone's hearing today. And that is about creating new insights from the data you have. So if you think about what the internet did was democratizing access to information, generative AI accessed or democratized knowledge, which is really powerful. But now we're going to be transitioning into software 4.0. And there's still 2 transitions left, 4.0 and 5.0. So 4.0 is what I'm referring to as a goal-oriented agent. It's going to be a specialized agent, and I think this thing is going to completely disrupt vertical SaaS. And then we have the next, which is 5.0, and that's an autonomous agent that can do a whole lot more DeepMind has been working towards this for about a decade. And we are now hitting the ceiling in terms of power consumption at data centers. We can't afford to keep building more. Because today, data centers consume, what, 3-4% of the world's power budget? Just with transformers today, and if we continue our current scaling trend and the current rate of deployment in industry, we're looking at about 20% of the world's energy just being used to power computers to run AI. So we can build better and funnier images.
And that sort of ties into my next question, Raymond, this rapid increase in growth of power consumption. So Raymond, compute and memory is a significant focus for many edge AI technology development. Why is this a fundamentally important technique to achieving AI goals of lower power, faster performance, and maybe touch on what we mean by edge AI?
Yes. First, let me touch on what's edge AI. Edge AI means anything that you carry. For example, think on your phone. For iPhone users, you have Siri, and when you talk to Siri, it answers to you, but the actual brain actually is in the cloud. So you rely on the 5G or whatever wireless network to transmit the data back and forth. And if you have the capability of Siri actually on your phone, that's edge AI. And my favorite example actually is Jarvis from Iron Man. And Iron Man carries Jarvis around, but Jarvis is still at his office. But the vision is, if you have edge AI, then Jarvis is always with the Iron Man suit, locally. There is also an implication of why do you need edge AI, for example, if the server and cloud can do the work. One point is that, as Jay is saying, like the data center is burning a lot of energy, and it actually is and will be becoming an energy crisis for there. And therefore, you want to minimize the energy usage as a data center, pushing some of the slighter load at AI inference work right at the edge, right on your device. The wearables, your headphones, your watches, your smartwatches, your phones, and that's kind of extreme edge. And sort of not so on the extreme edge, one big application would be autonomous driving in your vehicle. You want AI localized on your vehicle because you just can't afford the millisecond of delay going back and forth from your cloud to determine whether the sky is a plastic bag flowing in front of your car, or it's actually a child running across. So you need that split-second decision.
I'll give you an example. So I was working at a well-known self-driving company for a while. And because of the computational limitations at the edge, we had to squeeze down this model to a much smaller size, right? So we call this quantization, compression, pruning, and all these fun techniques. Now, what most people don't understand is the extraordinary amount of compute required to run these models at the number of frames that is required and the energy budget. And that dictates a lot of the constraints around that model. So I had an example where I had a 1 in a million probability of misclassifying a woman pushing a baby in the stroller across the street. It's a very specific example, and some people may have heard of this example. But after I quantized this model to try and deploy it, that became 1 in 10,000. And there was no way of understanding how that changed or what caused that change. And that's part of why we need better computer architectures that can deliver way more performance in these smaller energy budgets. Because the truest value of AI isn't going to be in the cloud. It is going to be when it's personalized, deployed at the edge with you. And that's why I love Microsoft's labeling of Copilot, because that's really what it is. It is not something that's going to replace you. It's going to amplify you, which is why my entire career has been about amplified and augmented intelligence, not artificial intelligence. And that's what the edge is ultimately going to do.
Yeah, and further to that point is how new architectures of building semiconductor for AI applications, AI accelerations is so important. And coming back to the point when Avinash was asking what about compute in memory, why compute in memory is so important. If you don't know what compute in memory is, This is really bringing the compute element really close or right inside the memory to avoid what Jay was mentioning earlier, the von Neumann architecture, which is traditional CPU architecture. We have your processor, your memory. You keep shipping data back and forth to do calculation, and then you're done, you put data back in. You just minimize that length of wire or connection, because most of the energy actually is, if you can believe me, is burned in that traffic. And compute in memory is one of the techniques to bring computation and the memory kind of fuse them together. There are multiple ways of doing that. People doing analog approaches, people doing digital approaches. In Untethered AI, we are kind of doing digital, but we brand ourselves, it's called at-memory approach. All these approach basically is the idea of bringing the processing, the multiplication, the matrix multiplication to the memory location so that you don't really ship data back and forth a lot.
Right. Completely separating the transition to the cloud and getting all the advantages if we're able to make more efficient, low power, faster responsiveness right at the local device itself.
Within the context of the edge computing. Yeah.
Thank you. Jay, slightly different take on questions here. Why aren't we seeing more later stage development out of the region, the broader geographic region in the area? We appear to have all the expertise and other building blocks to do this right here in the region, and yet we're still challenged.
Yeah, so it comes down to, I think most problems anywhere could come down to incentives. Right? If you understand the incentives, you'll figure out what's happening. In Canada, the incentive is pretty low to take risks. Now, as Raymond mentioned earlier, Canada's very cautious. We don't see a lot of deep tech and big challenges and problems, solutions to those challenges come out of Canada, because most investors want quick returns. They want their companies to exit within 5 years for a certain multiple, which seems ridiculous, or they want to do a SPAC and get their money out quick. Now, personally, I love deep tech for many reasons, and as Raymond mentioned, there's very few people that have the personality necessary to try and take on something that's a 10-year horizon and is going to require hundreds of millions of dollars to try and pursue, even though if it works, it's going to be game-changing. But that's not what we like here. Now, I'll give you an example. I started this company, and every investor I spoke to in Canada said, we don't do semiconductors, we don't like semiconductors. It's just too hard. It's also too expensive. I went to the US, it took me 2 weeks to raise my round. Right, so that's one of the big problems. We don't have the right incentives, we don't have the right structure to try and take on these big bets. But yes, we have the talent, and most of the talent recognizes this, so they're running off to the US, where they know that there are people that will support them.
That's why the hard tech investor
network is there.
And starting.
Hopefully we'll change that narrative.
Yeah, but can you raise $50 million from an angel round?
No. Well, we'll
not yet.
Get the first step going.
But
just
the same way we play to win in hockey, I'd love to see us play to win in the semiconductor space.
Would be nice.
It would be nice. And with that, I see that we've come to the conclusion of the time available to us. So I just wanted to express my gratitude to the panelists who gave their exceptional insights into this area. And please feel free to reach out to us to discuss more for those of you who may be interested. Thank you.
Thank you.
All I know is 10:35 and I'm thinking